Hello students, welcome to the course on engineering hydraulics, and today we are on the chapter on dimensional analysis. So this is the 10th lecture on the subject. Today we are going to study about the model investigation. What is the role of model investigation, why it is important, and firstly, what is a model? So you walk into a store, there you have spotted a car, a small car. Would you call that a model of a car or no? Well, for an engineering perspective, that is not a model. It is just a toy. So what criteria are there to classify an object as a model? Well, so that is what we're going to study today. To understand the importance of model investigation, let's understand why the model investigation is important. It is because it will let us understand how structure or the machine would behave when it is actually constructed. So prior to construction of a huge machine, just like a turbine or a hydropower dam, if we construct a model and do the investigation on it, then it will actually give us lots of information as of how it would behave when it is actually constructed. The next advantage is, if a problem cannot be solved analytically, a model developed to carry out experiment to solve that particular problem. Now, for example, you know it, for most of our calculation, we use the generic values, right? Like density for use 1000 kg per meter cube. Do you think it is true for all the cases? Well, no. So for analytical solving, we use predefined sets of values and which may not be the actual representative in the world. So for this reason, we first carry out experiment on the model, providing it with a similar situation that would persist in during the actual scenario. So here the model helps us to identify and solve the problem. Now let's define model. What is a model? A small replica of actual structure on a machine is known as model, and the actual machine or the structure is known as the prototype. Well, I have defined the model very loosely here. Like I said, you walk into a store, you spotted a small scale aeroplane, let's say. Would it be a model? Well, it is not a model, because for it to be classified as a model, it has to have some characteristics or property of the prototype which is representative or into a smaller scale. So that would be a model. So these similarities, there should be some similarities between prototype and a model, or else it will not be classified as models. The advantages of using models are: the behavior and working of a structure can be predicted beforehand, right? With the help of a model, how the actual prototype would behave in real situation, we could predict up to a certain degree, and then if there is a problem, we can rectify it. And with this is one of the advantage of the model. With the help of a model testing, number of alternative designs which facilitate in selection of most economical, safe, and accurate design at a little cost. So what it says is, let's say we have a problem. We are not a problem, but we want to construct a hydropower dam in Bhutan, let's say. So what kind of dam? What should be the height of the dam? And exactly what type of the dam would be much more accurate, and the cost will be less while we construct it. To find out this, what we do is we develop different types of model, and we do investigation, and based on the result we can conclude that this particular type of design is most suitable in our situation, and it is proving it to be cost effective. So in that scenario, we use model, because constructing a model is way cheaper than constructing a real time. And the third advantage is, now this is in case when existing structure is not functioning properly, then the defect can be detected and rectified by model testing. Now here, damage is already done. You have constructed a prototype or the project without doing any model investigation. Now there is a problem, let's say. the turbine is not running at the speed that which was supposed to you have designed it to run. Now, how to know the problem? Now, in real world, it would be very tedious to go and find and do every bits of experiment on the real thing. So for that, now the damage is already done. What we do is we try to replicate the same situation with the help of a model and try to understand what has gone wrong, and then we can propose the alternative solutions. Now, like I was stating in previously, all the object of the small scale cannot be considered as model, right? Because there has to be some similarities, and this similarities is known as similitude. There's types of similarities between model and prototype. So similitude is the types of similarities between model and prototype. There has to be some kind of similarities between model and the prototype before we call it a model. And these similarities are geometric similarities, kinematic similarities, and the dynamic similarities. Geometric similarity tells us that the ratio of the geometry has to be equal. Now, here is the numerical in the form of equation. The ratio of the length of the model and the length of the prototype, or the ratio of their length, should be equal to a ratio of their width should be equal to a ratio of a diameter. Now, if we are talking about a pipe, then yes, of course, the ratio would be the ratio of their diameter has to be equal, okay, for different conditions. Next one is kinematic similarities. By the term kinematic, it is something to do with motion, and it says path of the homologous moving particles are geometrically similar, or in other words, the ratio of velocity, acceleration of the homologous parts are equal for all different conditions. Now, velocity ratio in a simple term is the ratio of velocity of the model divided by velocity of the prototype. Now, what it is saying the homologous parts are equal is, now let's say in a model there's a discharge of 5 meter per second, okay, and the ratio, and as you increase the discharge for different experimental setup, the velocity of flow might change, but in the prototype, when you increase the discharge, similarly the ratio of the velocity in the model and the ratio of velocity in the prototype for different conditions must be same. Then only we call that particular model kinematically similar with the prototype. Similarly, acceleration ratio is the ratio of model to the prototype, and further you can go on defining acceleration in terms of the basic dimensions, and then we get the acceleration is nothing but the length ratio over the time ratio. Now, length ratio itself is the ratio of length of the model to the length of the prototype. Similarly, in velocity also I have expressed in terms of the basic dimensions, that is velocity is length over time, length ratio over time ratio, whereas length ratio is the length of model divided by length of prototype, and time is the time taken in the model divided by time taken in the prototype. Next type of similarities is the dynamic similarities. Now, for an object to be called, for it to be dynamically similar with the model, it's uh, it is to be first kinematically similar, plus if an object is geometrically similar to its prototype, then we call it dynamic similar, or in other terms, ratio of all the forces acting at a homologous parts are equal. Now here we come with a very interesting term, ratio of all the forces. Now this is what makes this topic very interesting, okay. In our previous section, we have discussed about the dimensionless terms while we do the dimensional analysis, right? Pi terms. We also call this as a pi terms. Now, a ratio of a force, the unit of force, Newton. When you divide a force divided by another type of another force, the unit is, there's no unit. So these ratios of force are nothing but these are pi terms. Okay, so we will discuss more about this more about the forces and their ratios in the next video. Thank you.